Okay, guys, looks most of the people are joined. So I'll start today's session. Last class we had discussed about latch timing analysis. So any queries, any questions from the previous session, guys? So we had discussed about latch timing analysis. That's nothing but your level sensitive timing analysis. We also call it time borrow analysis or cycle stealing analysis. Any queries, any questions, any opens from the previous session, folks? Okay. So today what we'll discuss, right? We'll discuss one of the complex topic, or I can say one of the complex and even one of the major complex and challenging topic in STA. That's nothing but your signal integrity or noise and crosstalk. Signal integrity. So today what we are going to discuss, right? What is signal integrity? Why we are seeing signal integrity? What are the classifications or what are the effects of signal integrity? Why we'll get the signal integrity? First of all, we'll understand what is signal integrity. Then we'll understand why signal integrity, or I can say SI analysis. Why SI analysis or why SI effects are introduced in lower technology nodes? Because of SI, what are the effects on your timing analysis? That's what we are going to discuss today, guys. So first thing, what by end of today's session, right, we'll understand what is signal integrity, or simply I can say what is SI. What is SI and why SI, or I can say why SI happen. Why SI happen in lower technology nodes? Why SI happens? Why SI happen in lower technology nodes? What are the SI effects in timing? What are the SI effects in timing? What are the SI effects in timing, guys? Anyone? Any idea? What are the SI effects in timing? SI effects in timing is nothing but your noise and crosstalk. Noise and a crosstalk.
Crosstalk and sir, antenna effect.
Antenna is not SI, guys. It's completely different. It's a reliability issue. It's not a part of signal integrity. Noise or crosstalk, these are the main things which are coming due to SI.
Electromigration.
No, electromigration, latch up, and antenna effect. Those are all your reliability issues.
Okay,
The
sir.
device issues. Antenna, latch up, EM, and ESD. Those are all reliability issues. Noise and crosstalk is completely different. It's completely different. It's under SI analysis. What is SI and what are the fixes? What are the remedies? And what are the fixes? What are the fixes? What are the fixes to noise and crosstalk? What are the fixes to noise and crosstalk? That's what we are going to discuss today, guys. These are the main things which we are going to discuss today. First of all, we'll understand what is SI. Why SI happen in lower technology node? Why can't be in older technology node like in 180 nanometer, 90 nanometer? Why SI analysis is not that much important? Then because of SI, what are the major effects in your timing? One is noise and another one is crosstalk. So then we'll discuss what is noise, what is crosstalk. Again, in the noise, again you have two types, like undershoot noise, uppershoot noise, or simply noise we can call glitch also. Noise we can call glitch also. So we'll discuss undershoot noise, uppershoot noise. Then again crosstalk, we have two types of crosstalk. One is positive crosstalk and another one is negative crosstalk. how the positive crosstalk will impact your setup on hold, how the negative crosstalk will impact your setup on hold slacks. So we'll get the answers for all these questions by end of this session, guys. Please stop me at any point of time if you have any queries. You can interrupt me at any point of time, guys. And again, try to concentrate more. Noise and crosstalk and signal integrity is one of the complex topic like CRPR, right? If you understand the basic fundamentals, then the fixes and the remedies and everything is easy. If you not understand the basic fundamentals, and if you are trying to by heart means, then you will be confused. Okay. And if you have any queries, any questions at any point of time, maybe you can stop me at any point of time, then we can discuss. So first of all, we'll discuss what is SI. Any idea, guys? What is SI? I'm saying signal integrity. What is SI? Maybe we'll come from a device physics, guys. What is SI? Any idea? What is SI? Okay, please open up. Like whatever you know, just we'll discuss.
Maintaining the same signal from source to destination without any distortion.
Sorry, can you repeat again? Can you repeat
Maintaining
again?
the same signal from.
Okay.
Yes, sir. Yes, sir.
Yeah.
I'm audible, sir.
Yeah, you are audible.
Maintaining the same signal from source to destination without any distortion.
Yeah, that's also correct. Yeah, maintaining the same signal without any distortion from source to destination. Yes, that is also correct. So you will have multiple effects. You have multiple signals which is going to distort the signal from source to destination. That's what we're going to understand. Okay, any other definition? Any other understanding, guys? Any other understanding?
Yes, sir.
Yeah. Any other understanding?
Sir, signal integrity is the ability of an electrical signal to carry information reliably and resist the effect of high frequency electromagnetic.
Yeah, it's a simple Google definition. So what does that mean? What's that means? Yeah, it's correct. Absolutely correct. Whatever you said, that's absolutely correct. Maybe I'll write whatever you said. So can you repeat? I'll write, then we'll discuss.
Sir, signal integrity.
Okay, signal integrity.
Basically, it is the ability of an electrical
Just give me
signal.
1 second. I'll try to write and we'll discuss. So it's the ability
of an electrical signal.
It's the ability of an electrical signal
to carry information.
Okay.
Reliably. And resist the effect of high frequency electromagnetic interference from nearby signal.
Resist the effects of, okay.
Resist the effect of high frequency.
Okay, resist the effects of
high frequency.
There is, okay, spelling mistake. Okay, resist the effects of high frequency.
EM interference. EM interference is electromagnetic.
Yeah, high frequency EM interference
from nearby signals.
From a nearby signals. I think whatever your friend said and whatever you are saying, both are same.
Yes, sir.
Nothing much different.
Yes, sir.
So what you said, it's the ability of an electrical signal to carry information reliably and resist the effects of high frequency of electromagnetic interference from a nearby signals. Or your friend said both are same.
Yeah, yes, sir.
Carry the signal without any distortion from source to destination. Both are same, guys. Whatever, maybe the statements which they are giving the different format, but yes, the entire meaning is same. That means if you have source and you have a destination, let's say Your signal is traversing from input port to output port. From the nearby signals, if you are seeing any effect of other signals, that's called signal integrity. Let's say, we'll understand by taking a simple example. Let's say you have one signal and you have another signal which is going, you have one net, we can call a net 1, we can call a net 2. Affecting of net 1 into net 2 or affecting of net 2 over to net 1. So affecting of one net to other net is called signal integrity. Affecting of one net to other net is called signal integrity. How it is going to affect, and because of how it is affecting, what is the major reason to affect, that we'll understand in detail now. So, but maybe if someone asks what is signal integrity, simply you can say affecting of one signal to other signal in a lower technology node is called signal integrity. I can say simply affecting of one signal to nearby other signal is called signal integrity. Affecting of one signal to nearby other signal is called signal integrity. So why it is affecting? What is the major reason? Why it is not happening in higher technology nodes? Why it is happening in lower technology node? What is the major reason? So guys, we'll take the simple example. Let's say if you are in 2000s, maybe we can go back to your 2000 century. So there, if you see your smart mobiles, if you look back your 2000 smart mobiles, there you won't see multiple options. Your camera might be the 2 megapixel, and video processing and the logic inside your processor, logic inside your mobile processor was very less. Why? The number of logic, the number of gates was used in 2000 mobile is very less, and then we have the less number of application. Now if you compare latest mobiles, if you compare the latest mobile which we are using in a 7 nanometer technology, if you compare today's Qualcomm 8555 or 8555 plus Snapdragon, how many number of, what is the gate count? Any idea? Millions of gate count we are using. Even one simple block also we are seeing 2 million gate count. Even I started my career where I have implemented one block with 0.5 million gate. Even nowadays, I'm implementing a block with a 3 to 4 million gate count in a simple block. So in a SOC, you have almost, if it is a big SOC, you will see hundreds of blocks. You will see 100 blocks. Then you can imagine what's your gate count. Then you can imagine, guys, what is your gate count? What is your gate count in the latest technology nodes? So if your gate count is increases, then what about your connectivity, guys? Okay, let's come this way. If your logic is increasing, your gate count will be increasing. If your gate count increase, what is the number of pins? Number of pins will increase or decrease?
Increased.
If the number of pins are increased, then it demands more routing connections, right? Let's say you have 100 cells. Let's say you have 100 pins, then it demands 100 connections. Let's say in our latest technology node or in recent days, in the latest technology nodes, we have 1000 pins, then 1000 connections are required, right? Again, the area wise, we are seeing the same area we are using. Same. So in the latest technology, so what I mean to say, in latest technology nodes, latest technology nodes gate count in the latest technology node due to demand of more applications the latest technology nodes with the demand of more applications, we are using more logic to meet specifications the demand of more application, we are using more logic and a more gate, so more logic to meet the specifications. So we are using more gate count. So we are using more gate count. It demands more connections. It demands a more connections with the same less area, the same area. Now you guys, you can understand in the older technology nodes, let's say you can imagine this way. You have a block, you have an area. In the older technology node, let's say like less than 45 nano, maybe you can imagine greater than 45 nanometer. You can imagine greater than 45 nanometer might be you are using in a simple block, we are using 0.5 million gate count. But in 7 nanometer, in the same area, in a 7 nanometer, we are using 5 million gate count. If you are using 5 million gate count, it increase number of connections to the same area, then it will increase the distance between the two signals, right? Let's say the 45 nanometer might be the distance between two signals is d. In the latest technology node, if you are using the same block in the same area, so because of increase of connectivity, might be connections will increase, might be number of connections will increase, and now you can see this d is very less. Distance between it is very less, it will be very less. So in latest technology nodes, the distance between signals will be dropped down enormously. So in latest technology nodes, space between signals are reduced, and it may affect other signals, or I can say space between signals are reduced, and it may form coupling capacitance. Again, it's a basic fundamental of physics, guys. If you have two signals, you have two conductors separated by a medium, what will happen? You have two conductors separated by medium, separated by insulator. What will happen, guys?
Charges get accumulated.
No, at least what will happen? How it affects?
Capacitor.
It's a capacitor. Simple basic fundamental of your physics, guys. If you have two conductors separated by a medium, let's say insulation medium, then it will form as a capacitor. Then there is a chance of charging and discharging. There is a possibility of charging and discharging. But it was not the case in older technology nodes, because your medium, the insulation medium is too high, which is not able to form the coupling capacitance. That's the reason people won't analyze the SI analysis greater than 45 technology nodes. And people will ignore the SI analysis on timing path in older technology nodes. People started analyzing SI. People started using of SI in a timing path from 45 nanometer technology, where we will see more connectivity and the distance between or the space between the connectivity has brought down very less. It was reduced very less, and it is able to form the coupling capacitance between the signals. So once the coupling capacitance is formed, and there is a chance of affecting of one signal to another signal. It's right. So if a coupling capacitance is formed, let's say you have coupling capacitance formed between these two signals, then there is a possibility of charging. If this signal has more energy and this signal has a less energy, then it may charge to signal 2. Or if the net 2 has a more energy compared to net 1, then net 2 may affect the net 1. It's all based on which net has a more driving strength, or which net having a more net length, which are accumulated more charges. Understand, guys, why signal integrity comes into the picture in the latest technology node, why it was not there in older technology node. Why it is? Because in the latest technology node, because of high logic, because of more logic, it demands more connectivity. Once it demands more connectivity, we will use a more number of connections in the same less area. Then the space between the routed nets, the space between the nets are reduced, and it's forming coupling capacitance between the signals. So because of the coupling capacitance, one signal, it's going to affect the nearby signals. So then we'll see effect of the same thing. Say SI analysis comes into the picture, it may affect nearby signals because of coupling capacitance. Understand, guys? Any questions, any doubts, any queries?
Sir, this the signal integrity affects the clock nets or data nets, sir?
Anything it can affect, right? Signal can be affected, clock and data, but clocks are more switching compared to data. Clocks are more switching, right?
Yes, sir.
Then the crosstalk or noise effects is more.
Okay.
See, you will have crosstalk or noise in both a data and clock, but a clock is switching, always switching. Data might be it's a constant, sometimes might be it may change, but a crosstalk will may affect a more on clock because it is always switching. That we'll understand in detail. That's the reason we go for NDR rules and shielding for clock nets at prior. During the CTS, during implementation of CTS, what people will follow, what the design engineer will follow, right? So it's kind of caring. So let us suppose what people will do. Normally people are in your daily life, if you have daily one apple, maybe it's it's good for your health, and you'll ignore to go to the hospital. The same here also. Before having, or I can say during the CTS, we'll take precautions to fix the crosstalk on clock nets. So by using NDR rules, by using shielding and some other methods we'll use to avoid crosstalk on clock nets. Okay. But crosstalk and SI analysis will be happening both clock and data. If someone asks, will your signal integrity or will your crosstalk or noise will impact only clock, or it may impact data also, then your answer should be both, sir. But clock is always switching, so there is a more chance happening in clock path. It might, that what I mean to say, right? Crosstalk impact more on clock path compared to data. It's because of switching always. Any other queries, guys? Yes, feel free to ask if you have anything. See, doubts are doubts, whether it is small or big. Even we can't classify the doubts. Whatever in your
Sir,
mind, you
what
can
are
throw it.
NDR rules, sir?
That we are going to discuss, Aisha.
Yeah, okay.
That we are going to discuss now. That means while I'm giving how we're going to fix the crosstalk. That time we'll discuss the NDR rules, non-default rules. We call non-default rules that we'll discuss now. Understand, guys? Any questions? At least, what is signal integrity? If you understand, then we'll go for what is noise and what is crosstalk. Let's try to concentrate. Again, if you are not concentrating here, again, if you go to your home, and again, if you are trying to read your own, it may take time. Crosstalk and noise analysis is not an easy thing. It's one of the complex topic. Just if you follow my lectures, right, it's a cakewalk. Like simply you can understand. Just try to follow my lectures, and you can, if you have any questions, any doubts, right, feel free to ask at any point of time. So yeah, then we'll move to next topic. What is noise? So now we understood what is signal integrity. So because of signal integrity, what is the impact on your timing paths? So the impact of timing path is noise and crosstalk. Guys, noise and crosstalk are the types of signal integrity. These two are the impacts of SI analysis, on timing paths, or I can say types of signal integrity. Simply I can mention impacts of SI analysis, impact of SI on timing paths, impacts of SI on timing paths. So we have two impacts, guys, majorly. Both are, one is a noise, or simply we can say glitch. Noise or glitch, both are same. Noise or glitch, both are same. Again, we have crosstalk. It's a crosstalk. So noise and crosstalk. Now we'll understand. Now we'll try to understand what is noise, and we'll understand what is noise. We'll take one simple example and we'll understand, guys. So let's say we have two nets. Let's say you have two nets are traveling for 100 microns. You have two nets which are traveling for 100 microns. You can say this is a net 1 and net 2. So if one signal is constant and so noise, right? Maybe I'll write the statement first, then we'll understand in detail. If one signal is constant and other signal is switching. If one signal is constant and other signal is switching. If one signal is constant and other signal is switching. Guys, I'm writing here switching, might be low to high or high to low. Anything is called switching. If one signal is constant and other signal is switching, then we can call noise. If one signal is constant and other signal is switching, then we can call that is a noise. And we can see here, let's say we'll take one example. You have two signals. This is a net 1 and net 2. Net 1 is constant. Net 2 is switching from logic 1 to logic 0, guys. We can see here. It's a switching logic 1 to logic 0. It's a switching logic 1 to logic 0. So here we're going to understand, we're going to understand two more technical terms. That is aggressor and victim. So the net which is affecting the other net, that's called aggressor. The net which is affecting other net, called aggressor. The net which is affected by other net is called victim. So the net the net which is affecting other net. The net which is affecting other net is called aggressor. The net which is affecting other net is called aggressor. The net which is affected by other net called victim. The simple, guys. Let's suppose we have two people. One we have more energy and another one other guy has a less energy. So if both are fighting, the guy who has a more energy can compete, or the guy who have more energy can beat the other guy. Let's suppose they are fighting. The guy who has a more energy can win. So similarly here. So let's suppose the one which is having the more energy. If one signal is constant and other signal is switching, then we call a noise. So let's suppose this is aggressor. This is the victim. We have net 2, which is switching from logic 1 to logic 0. And we have other net, which is a constant. Then there is a chance of, let's say, guys, what kind of noise you will see here? What kind of noise you will see? Your aggressor, say there is a chance of forming of coupling capacitance between these two nets. Because of coupling capacitance, your victim will try to follow the aggressor. Your victim will try to follow the aggressor. Sorry, your victim will try to follow the aggressor. So you can see here your aggressor is switching from logic 1 to logic 0. So your victim also will try to follow the aggressor this way. You can see if your aggressor is switching from logic 1 to logic 0, your victim also will try to follow the same thing. Then you can see undershoot noise. Then you can see undershoot noise. Understand, guys? See, if you see the location, or if you see the aggressor, right? Your aggressor is switching from logic 1 to logic 0. So what will happen? Your victim also will try to follow the aggressor, because aggressor having the more charges. So what is going to happen right here? The charge will be happen like this. Your aggressor will affect the victim. So victim will try to follow whatever aggressor is doing. So it will follow like this. And similarly, if you take another example, let's say you have victim net and you have aggressor net, it is try to switch this way. So let's say this is the aggressor. This is the victim. This is the victim. So what will happen here? Aggressor is switching from logic 0 to logic 1 in this time. So victim also will try to switch. From logic constants to logic 1. That's the reason you are getting some kind of noise or glitch. So what we can call this one, guys? What we can call this one?
Overshoot.
Overshoot. Simply we can say overshoot noise or overshoot glitch. Overshoot noise. So if one net is switching or another net is constant, then we can have noise or glitch based on your aggressor switching. We'll get whether it is an undershoot noise or uppershoot noise. So if aggressor is switching from logic 1 to logic 0, then you will see undershoot noise. If aggressor is switching from logic 0 to logic 1, then you will see overshoot noise. Understand, guys? What is noise? Any questions, any queries about noise? It's easy, just nothing, nothing here. Just if you simply understand your basic fundamentals, you'll get easily. Always like simple
Sir,
reason.
output transition time increases or delay increases, sir?
Sorry, output.
Transition time.
That we'll discuss. We'll discuss. See how it is going to happen. Your noise and how it is going to impact your cell delay. Finally, we are going to understand the cell delays, right? Finally, we are going to understand the cell delays. That's what we are going to understand. We'll understand the crosstalk. Based on the crosstalk, we are going to understand how your cell delay varies. See, if you see here, right, your transition will be varied, right? It's a simple reason your cell delays will increase because of the noise. Because you can see here, if you see earlier, your victim net is simply constant, but here it is switching and again it's going back. Then what is the meaning? It's your transition time, it may increase. Your transition time, it may increase. So if you understand, if you come to crosstalk, right, you'll understand easily that one. You'll understand in detail while you are doing the crosstalk. Let's say crosstalk. So crosstalk means if both the aggressor and a victim is switching. So if both aggressor and a victim, both aggressor and victim is switching, we have crosstalk. If both aggressor and victim is switching, then we have crosstalk. Then we have crosstalk. If both aggressor and victim is switching, then we have crosstalk. But if both aggressor and victim switching in same direction, if both aggressor and victim are switching in same direction, then what type of crosstalk we'll have, guys? It's a positive crosstalk or negative crosstalk?
Negative.
Positive crosstalk.
Positive crosstalk. Why it is positive, Aisha?
Both are switching at the same, no?
Yeah, it's both
At the
are
same
switching in
time.
the same direction. What is going to
Yes.
happen? If both aggressor and victim is switching, both aggressor and victim switching in same direction, then we have negative crosstalk. Why it is negative crosstalk, we'll understand. Negative crosstalk. If both aggressor and victim is switching in same direction, then we have negative crosstalk. If both aggressor and a victim switching in opposite direction, then we have positive crosstalk. Both aggressor and victim switching in opposite direction, we have positive crosstalk. We'll understand why it is negative crosstalk. Yeah, many people has a doubt. Both are switching in the same direction. Why it is negative crosstalk? It should be the positive crosstalk, right? Guys, again, it's one of the important interview question. People will try to confuse you. If you're not good at your fundamentals, then you during your interview, you will also confused. You should be stick to your basics and you should be very confident about your basic, whatever you are saying. If you are saying negative crosstalk, then you should be stick with your negative crosstalk. Then you need to explain why it is negative crosstalk. Let's say we'll take the same example. You have one signal, they're switching from high to low. You have another signal, they're switching from high to low. You have two signals. You have two signals, net 1 and net 2. Both are switching in the same direction, high to low. Let's say both are switching in high to low. Let's say this is aggressor. I can say this is aggressor. This is victim. If both are switching in the same direction, this is nothing but your transition only, right? So switching from one logic state to another logic state is nothing but your transition. The time taken from one logic state to another logic state, the time taken from logic 1 to logic 0 is called fall transition. The time taken from logic 0 to logic 1 we can call a rise transition. So we can call this is a fall transition. This is nothing but your transition only, right? So if both the nets are switching in the same direction, you have aggressor net and you have victim net. Because of the aggressor, your charge is going to, because of aggressor, your victim net will get the charge. So then your transition will increase or decrease? Your transition will increase or decrease, guys?
Increase.
Increase, sir.
Is it?
Increase, yes, sir.
Decreases.
Okay, I'll give a simple example, guys. Maybe here many of the people has known. Let's suppose you are participating in one running race. Maybe your friend Dilip is participating. Unfortunately, he has a big wind and you have a big airflow. What happened, right? Your airflow is from north to south and Dilip also running in north to south. His speed will increase or decrease?
Speed will increase, sir.
Speed will be increased, right?
Yeah.
Speed will be increased. Then he will reach the destination in a lesser time, or he will reach the destination in the lesser time or not?
Earlier, sir. We will reach destination
In
earlier.
lesser time.
If speed increases means the time taken to reach the destination will be less only, right?
Yeah, sir.
Then you people are saying here, if your transition is so here you need to compare your transition is with the time taken to reach the destination, right?
But sir,
Then how you
na,
are saying your transition will increase?
due to sir, your aggressor is from high to low, na,
Yes.
and victim is also high to low.
Yeah, victim also high to low. See what is going to
So
happen. See,
there will be some
see, let's say,
undershoot, na.
let's say here there is no undershoot, there is no overshoot, guys. See, you have victim net like this. Because of aggressor, see, both are switching in the same direction. So aggressor is affecting the victim net. Then what is going to happen? It will take more energy from aggressor, then it will reach your destination very fastly, right? Quickly it will reach the destination, whether it is right or wrong. It will reach the destination.
Yes, sir. Yes, sir.
It will reach the destination very fastly. Compared to earlier, it will reach the destination in a lesser time period, in a lesser time. Maybe you can take the same example, your friend participating in running race, or might be you can think one of your friend is bowling, one of your friend is bowling in the same direction of your wind flow. If you bowl in the same direction of your wind flow, your bowling speed will increase or decrease? Your bowling
Increase.
means it will be increase. Speed will be increased, but reaching the destination will be lesser. The same here. See, your transition is nothing but time taken to reach the destination. That may be lesser time, right? It take a less time to reach the destination from high to low. That's called the transition is going to reduce, not increased. If both are aggressor and victim are switching in the same direction, because of the coupling capacitance, you will see the charge will be, then you will see charge will be accumulated from aggressor to victim. Charge will be accumulated from aggressor to victim. It will be charged the victim net, then it will reach the destination quickly. It will reach the destination very quickly compared to earlier state. Guys, are you aligned with that statement or not? If you have any questions regarding the same statement, yes, I'll pause for a few seconds. You can think. This is the basic funda. If you're not understand this basic funda, right, you can't understand the crosstalk. If your aggressor and victim net are switching in the same direction, because of effect of your aggressor, victim net will reach the destination very quickly. That means your transition will be reduced. Transition will be reduced. You can see here the representation also. I represent the same thing. transition will be reduced after crosstalk. After crosstalk. So in a negative crosstalk, how the cell delays will be increased or decreased? So
Decrease.
transition reduced, then cell delays. Guys, cell delays. What is the relation between
Reduce.
transition and cell delays? We have
Directly
discussed multiple
proportional.
times. Directly proportional. So cell delays
Reduce.
decreased. So negative crosstalk will be benefit or demerits for your timing analysis.
Benefits.
Benefits. Negative crosstalk benefits for your setup slack. Now come for other type of crosstalk. If both threads are switching in opposite direction, let's say you have one signal, you have another signal. Okay, you have another signal. It is switching in opposite direction. So I can take, this is your switching time. Let's say this is aggressor, this is victim. This is aggressor and victim. So now how it will be impact on your victim net? Whether your victim net transition will increase or decreased. Maybe you can take the same example. Your friend participating in running a race, but unfortunately this time your wind flow is opposite to the candidate.
Transition increase.
Obviously, the transition will increase, right?
Cell delay will also increase.
So it will take the transition this way. You can see the transition are increasing. You can see how much the representation, how the transition. Now you can see, this is your transition time. This is your transition time after crosstalk. Impact of crosstalk or after crosstalk. So you can see the transition time increased. Transition time increased. Here you can see transition time increased. Transition time increased. Transition time increased. Transition time increased. So finally, cell delay increased or decreased? Finally, cell delay. If transition time is increased, what will happen to cell delay? Cell delay purely depends on input run and output load. Cell delay also. So finally, cell delay also increased. Understand, guys, how the negative crosstalk will reduce the cell delays and how a positive crosstalk will increase the cell delays. So now you understand why I'm calling this is a negative crosstalk. Why we are calling this is a negative crosstalk? We are reducing the cell delays.
Yes.
We are getting reduced cell delays. That's the reason I'm calling this is negative crosstalk. Finally, we are getting reduced cell delays. That's the reason we are calling this is negative crosstalk. And again here, if both the nets are switching in opposite direction, finally we are seeing cell delays are increased. So positive crosstalk. So the positive crosstalk and negative crosstalk are classified based on your cell delays, not based on your switching direction. I think Ayesha, you understood, right?
Yes,
now?
sir. Yes, sir.
So your crosstalk classification is based on your cell delays, not based on the direction. So positive crosstalk was done based on your cell delays, not based on your switching direction. So it's a negative crosstalk and it's a positive crosstalk. Understand, guys? Any questions, any doubts?
Sir, in noise delay, how
It always, right? Noise calculation is completely different, guys. It's not about your it's not about your crosstalk. It's not, sorry, it's not about your transition. Actually, if you join any company, right, crosstalk will be analyzed in prime time only. But for noise, right, they will do separate analysis. They'll do very, see, if someone asked which one is a more dangerous, noise or crosstalk, let's suppose you have some crosstalk violation, but you don't have any timing violations, but you have noise violation. Will you do the taping? Guys, I'm giving one scenario, simple scenario. Even I had asked multiple times the same question to the freshers or the people who are coming to the industry, who are having 1 or 2 years of experience. You have noise violations, you have crosstalk violations. You have noise violation and you have crosstalk violations. But you don't have a setup violation, you don't have a hold violation. Will you do the taping?
No.
Why?
No, sir.
Why? Yes, confidently he said no. But why?
Because noise, gives the differences in the correct output is not
Yeah. Just try to
represented.
explain. Yeah, whatever you are, maybe whatever you are analyzing in a good direction, Ayesha, just try to try to think more. Whatever you are saying is absolutely correct. Are you guys anytime anytime heard about noise margin?
Yes, sir. In inverter, sir. Inverter characteristic analysis.
Noise margin, guys. Noise margin. Anytime have you ever heard about noise margin? Anyone? Guys,
Sir,
it's a
in
basic fun.
uncertainty, the parameters are skew, jitter, and noise margin. There I heard noise margin.
No, that's what I'm asking. What is noise margin? That's what I'm
No, no,
asking.
sir.
Guys, maybe I don't know, like whether you people are reading the fundamentals or not.
Sir,
Device physics.
Effect of on output due to some jitter.
No, man. No, not at all. It's a basic funda. Okay, I'll ask the same question in a different way. Just 1 second. Okay. This is x-axis. This is y-axis. This is y-axis. This is x-axis and this is the y-axis. Let's say
Like we
0.
give the limit, sir.
It's a 0, it's a 1. Here, let's say a 0.2. Here it's a 0.98. How you will consider logic 0 and logic 1, guys? Any idea? Logic
Strong,
0 is okay. I'm not talking about strong 0, strong 1. In industry or somewhere, like let us suppose you are sampling the digital. How you will consider logic 0? If you get only 0, you will consider logic 0, or you have some margin. If your values are false between 0 to some other value, you will consider logic 0.
VIL to VIH.
Yeah, what is that? Yeah, I'm not talking about.
Like, yes, sir.
I'm
We
not asking
give
about
certain
the definition.
limits in that will take as 0. We give certain limits in that will take as
Absolutely correct. That means we are not going to consider logic 0 is exactly 0. What are the values false between some limit? Let's suppose the values while you are doing sampling, right? See, while you are doing sampling from analog to digital, the values falls between this region we can call logic 0. This is a logic 0. This one we can call logic 1. This is called noise margin, guys. These regions we can call noise margins. So whatever you are saying 0 to 0.2, it's a noise margin for logic 0. 0.98 to 1, it's a noise margin for logic 1. That means if the values falls between 0 to 0.2, we can consider the logic 0. If the value falls between 0.98 to 1, we can call it a logic 1. Let us suppose you have noise. Unfortunately, we are getting actually this is logic 0. Let's suppose this is logic 1. Let us suppose victim net is logic 1, but you have undershoot noise. So because of that your noise, right, it's reaching 0.1. Then what tool will consider? Will it consider logic 0? Obviously it will consider logic 0, right? Because of your noise, because of your glitch, for some time period actually it is logic 1, but because of the noise, because of the glitch, it falls in the region of your logic 0 threshold. Then what is going to happen, guys? What is going to happen? Tool or data, it may go to the metastability, right? It may go to the metastability. Actual, your expected output is logic 1. Because of the noise, we are getting logic 0. The false output you are getting. They are getting false output. So noise is more dangerous than crosstalk. So if you have the noise violation, we should fix the noise violations. If you have crosstalk violation, might be crosstalk, it's going to impact your timing. Crosstalk, it may degrade your setup violation. Crosstalk, it may degrade your hold violations. But it won't go to the metastability because of the crosstalk. But if you have the noise violation, there is a chance of data will go to the metastability. Metastability means we can't predict the output, whether will you get logic 1 or logic 0. But here in this same case example, which we are discussing, we are expecting logic 1, but for some time period, you may get logic 0 because of the noise. So that's the reason we should fix the noises. Understand, guys? Understand, Aisha?
Yes, sir. Yes, sir.
So this is called noise margin concept. Guys, just you can Google, you will find multiple articles for noise margin, but it's one of the important topic. Maybe if you're about to join the physical design engineer, means you should understand what is noise margin. Without understanding noise margin, you can't understand the noise violations. What is the importance of the noise violation? What is the significance of the noise violation? Why we need to fix the noise violations? Noise violations are more dangerous than crosstalk. That's the reason people won't do tape in if you have the noise violation. If you have crosstalk violation, we'll do tape in. But if you have the noise violation, people won't accept to do the tape in. Understand, guys? Any questions, any queries regarding noise and crosstalk, guys? Okay, so with this, maybe I'll stop for today, guys. With this note, I'll stop for today's session. I'll end today's session. Tomorrow, right, we'll discuss what are the fixing methods, what are the fixing methods for noise and crosstalk. What are the ways to fix the noise and crosstalk? How you will fix the noise and crosstalk? There might be we are going to discuss NDR rules, shielding. We'll do the shielding with a VDD and VSS. So among ground and power, which one is more useful to fix the crosstalk? Will you use ground as a shielding or power nets? And again, we'll understand other methods also, how to fix the crosstalk, like adding buffers in the victim net, or downsize the aggressor driver, or upsize the victim driver. So all those methods we'll discuss in detail tomorrow session. Okay. So I'll stop for now, guys. Maybe we'll meet tomorrow at the same time. Any questions, guys, before ending for today?
No, sir.
Others? Yes, I'm not hearing anything from others.
No, sir.
Shahrukh,
Sir,
Akhil,
sir,
Girish. Yeah. Any questions, Girish?
nothing in this topic, sir. Sir, when you'll start the tools, sir?
Once the STA might be by end of next week. I think we left only with advanced topics of STA, like timing exceptions, multi-cycle paths, and then might be it will take another 2 to 3 sessions, guys. Once the noise crosstalk is done, one day we'll discuss about might be timing exceptions. One is false path, case analysis. Yeah, false path, case analysis, and synchronous and asynchronous clocks will take one session. Multi-cycle path will take a one session. Yeah, maximum 3 sessions, guys. At max, I'll take another 3 sessions to complete your STA. Thereafter, we'll start the tool. So in the next 3 sessions, we're going to discuss advanced topics like advanced STA. So it's about timing exceptions. Like what is multi-cycle path? What are the different types of multi-cycle path? What are the false path? Then what is synchronous clocks, asynchronous clocks, case analysis, disable timing arcs. So difference between all those timing exceptions. Then we'll discuss about GBA and PBA method. Then we'll discuss about how to fix the setup violation and how to fix the whole violation. Have you discussed about useful skew method, guys? Useful skew, positive skew and negative skew. There is yes or not, guys? I'm not hearing anything.
No, sir.
Okay, yeah, maybe. Okay, we'll discuss that also. So we left with some advanced STA. At max, it will take 3 to 4 sessions, guys. At max, it will take another 3 to 4 sessions to start your tool. Again,
Sir,
the tool, right? We'll start with the Unix environment. Yes, Girish, you are trying to say something?
Nothing, sir. Like tomorrow, anyhow, it is Saturday now, sir. You can take for more than 1 hour.
Yeah, I'll take. See, today also, I think we have taken almost more than an hour. We'll spend more time.
So tomorrow class timing?
The same, like at 7.
Sir, we will discuss about ECO.
Yeah, we'll discuss about ECOs. It's
Yes,
not
sir.
ECA, it's ECO.
Okay. Yeah, ECO. Yeah.
Yeah, ECOs. We'll discuss about ECOs also. Any other questions, guys? Yeah, any queries?
Sir, clock domain crossing.
CDC, right? We'll discuss while we are doing during CTS. Not now. We'll discuss during CTS, clock domain crossing.
Okay, sir.
Yeah. While we are doing CTS, right? We'll have some time because
And
yes, if
GBA and PBA, sir.
yeah, that's what
GBA.
I said right just now. We left with
Yes.
GBA and PBA method and useful skew method and timing exceptions. These are the 3 topics we need to cover in the next sessions. Okay, that's all I have for today's session, guys. We'll meet tomorrow. We'll meet tomorrow at the same time, 7 p.m. If any time slot changes, right, I'll let you know at upfront. Okay, guys. Yeah, I have done for today. We'll meet tomorrow. Thank you, guys.
Thank you, sir.
Thank you, sir.
Yeah, bye.